Today's topics are haloform reactions and alkylation of enamines. So we can attempt alpha halogenation under equilibrium basic conditions. This is a base-promoted reaction and it will lead to a formation of an enolate, which is not favored, but the equilibrium step is pushed forward by the favorable halogenation step. And the question here is, will the presence of an alpha bromine make the remaining alpha proton more or less acidic? And the answer is, it will be more acidic. So we'd like to point out that monohalogenations are not possible under basic conditions because the alpha haloketone produced is more reactive than the ketone, and the second halogenation will occur faster than the first, and the third halogenation will be even faster. Because of this tendency for multiple halogenations, base-promoted halogenation is not used to prepare monohalogenated ketones. Methyl ketones can be converted to carboxylic acids using excess hydroxide and dihalogen. So we will show this mechanism in further detail. After all three alpha protons have reacted, the new CBr3 group is a moderately good leaving group. And now we'll show the mechanism. Please note that this reaction works well with Cl2, Br2, and I2. Thus, it is generically called the haloform reaction. The first part of the haloform reaction will be an alpha halogenation under equilibrium basic conditions. So the OH is going to deprotonate the alpha carbon, which will result in an anion in the second step. And then these electrons will form a bond with the bromine, and resulting from that will be a bromine on this carbon and two alpha hydrogens left. This mechanism will occur two more times until these hydrogens also get replaced by bromine, and as a result we'll get CBr3, which is a good leaving group. So here we have this molecule with the CBr3 that resulted from the three halogenations as shown previously, and this is our fourth equivalent of the OH minus from the base. So this will come attack this carbon here, and the electrons from this pi bond will go up to the oxygen, and we will get this molecule as a result. The electrons from this O will come back down to form a pi bond again, and CBr3 is a good leaving group, so it will leave, and electrons will go onto the C, and we will get these two molecules as a result. And the electrons from the C will deprotonate this O, and the electrons will go to the O, and we will get the anion on oxygen anion here, and a bromoform molecule, which is an example of a haloform reaction.
We've talked to you about the haloform reaction. We want to move on and talk about the alkylation of enamines. What you have here on this slide is a review of the mechanism of enamine formation. In the interest of time, we will not review this mechanism, but feel free to review it on your own. So what we have here is a nucleophilic carbon at the alpha position. This nucleophilic carbon will be used to attack an electrophile, forming a new bond between the nucleophilic carbon and the electrophile. This process is referred to as alkylation, or adding a group to that carbon. We will proceed through the mechanism now. So the alkylation of an enamine begins with an enamine. We have shown the resonance structure here so that you can see how the alpha carbon here is nucleophilic. So what you have is, to form the resonance structure, is the lone pair on this nitrogen coming down to form a pi bond here, and the pi bond dropping the lone pair of electrons onto this carbon. So you can see here the formation of an anion nucleophilic carbon at the alpha position. Over here with this reagent, we have the bond between bromine and carbon here, dropping the lone pair onto this bromine, and this will leave a positively charged cation here at this carbon, which will be electrophilic and will be attacked by the nucleophilic carbon at the alpha position. What you have is the formation of an iminium salt intermediate with a positive charge on the nitrogen and the CH2 phenyl group added to the molecule. Also floating around will be the Br minus in solution. And so to get from this iminium salt intermediate to the ketone, the alkylated ketone product, we will push this reaction with the addition of H3O plus through a hydrolysis reaction to return back to the ketone alkylated product. So what we have here, you can review the mechanism previously covered in class, is a hydrolysis reaction to produce the alkylated ketone product and the cyclic byproduct, and thus is the enamine alkylation reaction. So that wraps up our discussion today of haloform reactions and the alkylation of enamines. If you have any questions for us, please ask now.